Okay, you're live.
When we look up in the night sky, the stars seem eternal. In some senses, they are to a human lifetime, but stars, like people, are born, they live, and eventually die. Of all areas of modern astrophysics, our knowledge of how stars work is arguably the most complete and well understood of any physical phenomena in the cosmos. So when a star just disappears, astronomers are left scratching their heads as to why and what natural or artificial event has just occurred. Now, you could say that losing one star is just careless, but when comparing sky surveys of 70 years ago to recent studies, it turns out that as many as 100 stars may have vanished. So the question is, how well do we really know stars, and what or who is responsible for these extraordinary findings? Good morning, good evening, good afternoon to everybody, and welcome to the April 2021 edition of SETI Talks. My name is Simon Steele. I'm the Senior Director of Education Outreach at the SETI Institute. The SETI Institute has been holding these monthly talks on cutting-edge topics of astronomy and the search for life in the universe for over 10 years. For most of this time, the talks are in person in downtown Silicon Valley, but a silver lining to this current pandemic means that as we're now virtual, we're able to reach audiences across the globe. So please do type into chat or onto Facebook, let us know where you're tuning in from. We also welcome your questions. Type them into the Q&A function on Zoom or comment on Facebook and YouTube. We have behind the scenes Frank and Rebecca, who are going to pass these questions on to the panelists at the end, but please hold off on your questions until the moderator gives you the nod. We won't get to them all, but we'll do our best to get to the good ones and the exciting ones and the controversial ones. Without further ado, I'm very pleased to welcome two astronomers who are going to dig deep into a case worthy of the great Sherlock Holmes, the mystery of vanishing stars. And I'm going to hand you over now to our moderator of the evening and the conversation, and a star that shows no signs of dimming himself, the SETI Institute's senior astronomer, Seth Shostak. Take it away, Seth.
Thank you very much, Simon. And in fact, I'll turn up the light here just to avoid any dimming here. This is going to be an interesting talk tonight. I mean, I may tell you that all the time, but it really will be, because we're not going to be doing the usual colloquium where somebody might discuss the effects of inverse Compton scattering on the line widths of forbidden transitions and white dwarfs. I know you're interested in that kind of stuff, but that's not what we're going to talk about. We're going to talk about what seems like a very simple experiment. Of course, it's not really simple, but it's one you can understand right away, a simple experiment with an extremely profound potential consequence. So this will be really something different. Before introducing the speakers and getting right into it, then let me acknowledge the behind the scenes SETI Institute employees who make these talks possible. Rebecca McDonald, Lee, Jasmine Hedges, and very especially Frank Marchese. I'm Seth Shostak, and I'm a senior astronomer at the SETI Institute. And let me be so brazen as to point out that the SETI Institute has been doing these talks for a long time. You just heard about that. But the SETI Institute is a nonprofit. So if you would like to encourage these efforts to shamelessly sell the kind of science we're doing and the science that others are doing, if you would like to help out on that, just go to the SETI Institute's website, seti.org, and weigh in on that. Okay, let's now meet our two speakers. I'll give a brief introduction for each. And after I've done that, they will each have a couple of minutes to tell you something about what they've done. The first is Beatriz Villaroel. I will mangle her name consistently, but not always the same way. She's a principal investigator of the Vanishing and Appearing Sources during a Century of Observations project. That makes an acronym, VASCO. I can't get it right either. VASCO. And that's the winner of the Milpitas Prize for Convoluted Acronyms. Beatriz got her PhD from Uppsala University and did a postdoc at ETH. That's the Swiss Federal Institute of Technology in Zurich. Since 2018, she's been a postdoctoral researcher at Nordita in Stockholm and IAC at Tenerife, Spanish island. She's been a postdoctoral researcher at Nordita. She's been a postdoctoral researcher at Nordita in Stockholm from, well, I don't know how many years, but this year, Beatriz received the L'Oreal UNESCO Prize for Women in Science in Sweden for her VASCO work. James Davenport is a research assistant professor of astronomy at the University of Washington and the associate director of the DIRAC. Now, that's another convoluted acronym for the Data Intensive Research in Cosmology Institute. He specializes in survey astronomy, using large volumes of data from telescopes worldwide to study nearby stars in the Milky Way. He's an expert in the magnetically regulated activity of stars, including hot flares and cool spots, and how these events may impact life. He's also become an advocate for using big data techniques to search for intelligent life in the universe, and I'm sure we're going to hear about that. Okay, those are the abbreviated bios, but what about the work? Each of the speakers will now spend 4 minutes each talking about their research, after which we'll have a knockdown, drag-out discussion in which we hope to elucidate for you what's really important in this effort. Okay, Beatriz, the Zoom room is yours.
Okay, so I'm going to share the screen. How does one do now? I think I did it in the opposite direction. So let's try.
Share their screens.
Yes. So I will. Stars, I have seen them fall, but when they drop and die, no star is lost at all from all the star-sown sky. Now, this is a poem by a British poet that shows his view of the night sky. Today, we know that if a star dies, either it transforms over billions of years into a white dwarf, or perhaps it explodes in a bright supernova. But could a star actually just vanish, or could any object on the sky just vanish? This is something I've been thinking about since I was an undergraduate student. I was really wondering about this for a long time until I, as a PhD student, found a way actually how one could check it. And this is how the VASCO project was born. In the VASCO project, we are actually searching for vanishing stars by comparing data from the 1950s to data from today. And we are hoping to find our ideal candidate, which is a star that has been there and you see it in many images, and later, like now, has completely vanished. Because our ideal candidate could basically be a technosignature, a signature of stellar engineering, because we don't know of any processes that would make stars vanishing in the Milky Way today, except for the hypothetical idea of possible failed supernova. However, in the VASCO project, we also have an initial candidate selection where we select anything that could have been seen in the catalogs from the 1950s and are not seen today anymore. This includes a lot of natural phenomena like optical afterglows of gamma ray bursts, variable stars, maybe flares of M dwarfs, variable quasars and acting galactic nuclei. Actually, also other type of technosignatures can enter, like a communication laser might give rise to a short transient event, etc. So this is what goes into the initial VASCO candidate selection. So have we found anything yet? We have 100 initial candidates. Indeed, here you can see an image from the 1955. This is from the post-1 data. You see something here. You do not see it in the 80s. You do not see it in 2000 plus. You do not see it in the most recent catalogs. We have here another candidate. It is seen in 1953. Actually, it's still seen in the 80s, but it's not seen later in the SDSS nor in Pan-STARRS, which is the most recent. And so on, we can get around 100 of candidates where most are only seen in one image from the 1950s. Here's another example. I think this one is quite pretty. It's seen there, it's not seen there. And here we see another one, and it's not seen there either. So what do we think they are? We think that these are short-lived transient events that were only lasting for a few minutes, not really a star that has vanished, most of them. And in these cases, we are trying to understand what are these short-lived transient events. We have excluded asteroids, we have excluded variable stars, we have excluded variable AGN for this, and we have excluded a lot of different things. And what we are left with are optical afterglows of gamma ray bursts, of fast radio bursts, and we're also left with still the possibility that this might be M dwarf flares. And we're working on it, submitting proposals to try to understand what we have seen. And we are still searching for the ideal candidate by improving our methods and the citizen science project. These were my 4 minutes.
Okay, Beatriz, thank you very much. And the floor is now yours, James.
I will stop sharing.
Great, I will switch on my sharing here. Good morning from a very sunny Seattle. There we go. And I'll just spend a couple minutes talking about, sort of complement what Beatriz talked about. What I'd say SETI with big data astronomy, what I think is the future, or I hope is the future. So I, like Beatriz, I got interested in this early on in my career, and it's something that's been in the back of my mind as I've developed as an astronomer. And it's this idea of using these large catalogs, these large surveys, and these giant telescopes and giant data sets to search for the truly spectacular and the unknown. Now, a survey that we work a lot with and are helping develop at the University of Washington is the Vera Rubin Observatory, which is going to run the legacy survey of space and time, or we just call it LSST. Now, here is the computer rendering of what this will look like. Here's a person for scale. So this is roughly a house-sized telescope that's going to survey the night sky every 3 nights in Chile. And we'll do so for about 10 years. Now, this is great PR imagery, yep, flying through outer space, all fantastic. But what makes me really excited is here is actual footage, a nice little drone shot of them installing the top end, or so the top section, the top mirror of the telescope. This is an 8.4 meter telescope. They had to get the largest crane available in Chile up onto the mountain to do this. It's a massive engineering feat. And it's a really spectacular data set, which will revolutionize effectively all of modern astronomy. This will be the great sort of data tide that lifts all the science boats from the stars, from the galaxies, looking for planets. It will do everything. But most excited for me is that this is a massive data set that will help us explore the sky regularly every night. So something like 17 billion stars will be observed over a course of 10 years. That's 20 terabytes of data, give or take a night, something like 10 to 15 petabytes of data over the survey. This is a giant imaging survey that takes, and so you can see this map of the sky that it'll photograph over and over and over. And what I think is so special about this is not just this enormous catalog of images, but this becomes this sort of portal for astronomers to not have to go to the telescope, but instead to run our experiments through our computers. And so the game is not to travel to the telescope and to take one picture of one object anymore. It's instead to write algorithms, to write software, to search through 17 billion or more of these objects to look for the things that are strange. And I think this is the true revolution in SETI, is we'll be able to do SETI projects over effectively the entire sky all the time. What makes me so excited about the VASCO project, and I'm so excited to talk here today with Beatriz, is that I think it's one of the best and simplest SETI projects that have ever been developed. Here, I've just stolen some of the images from her fantastic paper. And what we're possibly looking for here, in the most optimistic case, is something like a Dyson sphere or some kind of mega structure that's been created. And we would say, as an astronomer, we would look at some chart like this of brightness over time, and we're looking for something that drops off. So instead of analyzing images from these big surveys, we're looking for something that's got lots of measurements, and then it falls off a cliff. The star appears to disappear. And what we can do with LSST, or big surveys like it, is look for new candidates. We can use this kind of shape of the event that we're looking for. We can write software that's going to look for these kinds of events, and we can check on these old candidates. This is an 8-meter telescope. This is one of the largest telescopes in the world, and it's going to allow us to go back to all these candidates that Beatriz and others are generating and get new data at even fainter limits to see what's going on with these stars. Are they still there? Are they still changing? Or have they truly disappeared? And finally, what I just say is that this is one of many possible experiments that we can run with surveys like the LSST. We're searching for 17 billion stars to do something that we don't expect. And on top of that, there'll be transient or sort of flashes of things that are unexpected. The night sky, this will be a movie of the night sky that will truly be revolutionary. And so I'm really excited to try to develop these new ideas.
All right, James, thank you very much. Beatriz, thank you. And now, you're no longer going to be in control of the conversation, because we're going to grill you with a couple of questions. And by the way, to those watching, you will have your chance to ask questions later on. But let's begin with you, Beatriz. Okay, this work where you study the behavior or the appearance of millions, I think, stars. You didn't say how many objects, but it's somewhat reminiscent of clinical trials of, for example, the vaccine for COVID, right? You have tens of thousands of people that get the thing. And the reason you do that is to find effects that only might be at the 0.1% level, right? 1 in 1,000 people have this kind of a reaction. So you're looking at a lot of candidates and to see which ones, have done something, and you found 100 that did something. So my question to you is that, all right, you're talking about stars that have disappeared, but surely it could have been that, the stars were also disappeared, as it were, before the Palomar sky survey photos were made. And in fact, what you found was an appearing star. We know about appearing stars, novae, that sort of thing. Have you, sort of considered that and tried to figure out, well, how many appearing stars would I expect to find anyway?
So let me just reiterate if I understood your question correctly. You mean in case we do these surveys, if we can find also a number of appearing stars?
Yes.
Well, in the cross-match we have done right now, we have only specifically looked for vanishing things. We have required all the objects that were there in the 50s to have vanished in the new ones. In order to do the experiment the other way, we will have to turn around the process.
But I guess my point is only that if you had made photos, if you had a survey from the 1940s, for example, you might not have found these 100 objects either.
Yes, exactly. So actually the 100 objects we have might have been something, not actually stars. We think that most of these are something that just appeared very shortly and were taken on an image in the 50s and then vanished. So it's actually not a star per se, it's an event more than a star.
Okay, and have you estimated how many, for example, novae or supernovae you would expect to find in an experiment like this?
Not really. We have planning to do that. We have a theoretician who is going to look into that.
Okay, great.
We estimated the number of failed supernova we expected, and that was basically nothing.
Yeah, but there are novae and flares and stuff like that.
Yeah, sure. Those one can expect, but supernova in the Milky Way, we're only looking at Milky Way data. I mean, it's 1 per 100. The last one was 100 years ago, so we don't expect anything to be found in the supernova direction in the Milky Way or in this data set at least.
Okay. All right. Let me ask you something, James. VASCO shows that the sort of discovery that demonstrates the kind of discovery that can be made with very large samples. Heck, the most important astronomy discovery, I guess, of the 20th century, the Hertzsprung-Russell diagram, which explained, the nature of stars in many ways. And it was only done once we had, in the late 19th century, when there was just this massive amount of photographic spectra of stars, right? That led to, I guess it was Cecilia Payne-Gaposchkin, went through these things, categorized them. Suddenly, we knew a lot more about the behavior of stars. And it was just because all these glass plates were stacked up, okay? So we're gonna have a lot of data here from the Vera Rubin telescope. You just told us about that. And we can see things that change over the course of days, not necessarily decades. It's totally unexplored territory. Do you have any expectation that it will be fruitful other than the usual expectation? It's a new instrument, we'll find something new.
I mean, that's right. At first blush, whenever we go into a new realm of data, a new wavelength regime, if we go to the infrared or to the ultraviolet or the radio, whenever we go anywhere new, we find new things. We have been consistently surprised by the unexpected in astronomy. And so that's good job security for us, which is great. I do think there's a lot of opportunity with the Rubin Observatory and other big telescopes, big surveys, to discover what we don't expect from normal stars. And I think a great example of this is something that came from the Kepler mission, which I know the SETI Institute has talked about, which is like Boyajian star. Here is a apparently very normal looking F-type star, slightly more massive star than our sun, that one day decided to do something very bizarre. And we're still arguing about it almost 10 years later about was it comets or was it dust or was it a bunch of moons? We do think this is not a Dyson sphere or an alien megastructure, but it is totally new behavior for this kind of star. So we can almost guarantee that we're going to see things like this in these data sets. And I like your use of the Hertzsprung-Russell diagram, because It's something that pops out that tells this story of how stars live and die and evolve. And it comes both, as you said, from a large set of data, but also it comes when we learn how to sort our data, how to make that graph, how to which axes on the graph to look at. Those kinds of innovations pop out when you start taking new kinds of data. In that case, it was taking these, as you said, big surveys of spectra and colors and brightnesses. We're taking all new kinds of measurements. This is a precision instrument which takes measurements in time. And so what will be the new Hertzsprung-Russell diagram where we sort a billion dots to look for the strange outliers in time or in color or in variations? I don't know. We won't know what those revelations will be until we take that giant catalog and just cut it every possible way we can think of.
All right. So clearly, I mean, you seem to be convinced, and I think justifiably, that bringing on this new telescope, not that it's the biggest telescope in the world, not that it operates at particular wavelengths that haven't been looked at before, but simply by photographing the night sky as much as you can see there, every 3 days, there are going to be big discoveries. Right?
Yeah, I mean, how about this? I'm betting my career on it, right? we're all very vested in this. This is one of the top funded priorities for astronomy worldwide, because we do think it is going to, as I said, lift all scientific boats. We're going to discover new kinds of supernova and transients. We're going to make the best estimate of Planet Nine's existence. We're going to look for things that go bump in the night that we've never even thought to look, because we never looked for that long, because nobody had one telescope doing this for a decade. We're starting to look at things that change over a human lifetime. And I think that's going to be really unique.
Yeah, I think it's also the case that you couldn't have done this 30 years ago because you had photographic plates for imaging, and they were much less sensitive, of course, but you also couldn't make, thousands of photos every night.
That's right. And we couldn't have processed them. I mean, one of the unique things that the LSST will produce not only is this image of the night sky every 3 nights, but anything that it detects that changes between visits, it will publish in real time within 1 minute. So if you are another telescope looking for a particular kind of supernova or asteroid, and the LSST project observes one, within a minute, they will publish an alert in real time on the internet that anybody who is any other telescope who's interested in these kinds of events can go and chase. So it really is kind of this democratization of the access to the night sky with this massive telescope. Those kinds of facilities are only available because we have the internet, because we have large computers, because 10 to 15 petabytes of data, while it's too big for my laptop, is not too big for the giant cloud servers to handle. So it really is a great moment in time where we can actually crunch these numbers for the first time.
All right, back to you, Beatriz. Someone could argue that the VASCO project is the most important SETI experiment going. I mean, SETI has traditionally looked for signals, radio signals, flashing lasers, stuff like that. And there could be societies out there that are millions or billions of years more advanced than we are. Maybe for whatever reason, they don't flash lights into the sky, or maybe they don't send signals that by chance happen to arrive at our antennas just in the couple of minutes that we're actually looking for them. So what you're doing is it seems that it's the best way to look for those societies that are way more advanced than we are, but, might be 1,000 light years away, that sort of thing. They could make a change to the cosmos after all. I mean, these putative societies that are very big. We've talked a little bit here about Dyson spheres, but I mean, that's a 20th century idea. There are probably 23rd century ideas that will be just as impressive. So do you think that, you sort of implied this, that such activities have already taken place, that the aliens, some aliens, the best aliens, if you will, have already done something that you could pick up this way?
Well, I'm an optimist. I wouldn't be looking for ET unless I believe that they have already created visible technosignatures. So I guess that there might be quite a lot of technosignatures out there. And let's say that, let's make an example. I'm going to just a mind experiment. Let's say ET has been very interested in our Earth for whatever reason, sent here a lot of probes, some, 100,000 years ago, or 10,000 years ago, just to make it slightly more contemporary. And possibly these probes could be floating around in our solar system. And one of the things that one would be able to pick up, it would be something that looks like satellite glints in the 1950s, for example. And these kind of things we could be able to pick up with VASCO today. If someone will try to use modern data, most of these things will be confused with human-made things. So this is one of the things that one could actually pick up in a rather short time scale, if it would exist, as an example.
Can you give us some idea of the sensitivity of the experiment? Obviously, the dimmest thing you can recognize depends on how far away it is, but within 200 light years of the VASCO experiment, within 200 light years distance, you have 1 million star systems. So, how faint could a star be and still show up in this kind of an experiment? Or is it, severely limited that way?
Well, the USNO catalog has a limit of 20 mag in the R band.
Yeah, that may not mean too much to people.
Exactly.
Do you know at what distance would the sun appear to be 20th magnitude?
Oh, now with this quick stress, I will give you a random number.
Okay. But I mean, that's maybe the first reaction that people say that, yes. Okay, this is a nice idea, but clearly, if you're not at least as bright as a star, we'll not see you, ET.
Yes.
You don't agree with that, do you?
Sorry, what did you say?
Do you agree with that radical statement? I mean,
that we might not see ET, or
yeah.
I think I don't quite follow. Could you repeat the last?
Okay, no, I won't torture you anymore with this question. No, I mean, people can very easily tell you, for example, if you're doing an experiment with this antenna over here trying to find a signal,
yes,
right, and it's coming from a couple of hundred light years away, you can sort of, reverse that argument and say, well, how much power do they need for us to be able to see that? And this experiment seems to be working on the scale of, stars. In other words, things that people don't build, presumably. And so I just wanted, if you have any indication of this.
We already have the technology like on Earth in order to produce something visible for those who are far away from us. I mean, the lasers we have today, if we really would want to, I'm sure we could just direct one laser in one direction and hope that someone picks it up. But why would we do that? Why would we waste energy if we don't even know where we would beam it? Yeah. So when it's a lot of luck, it's it's a big space.
James, once you get going on this VASCO-like experiment using the Vera Rubin telescope, how often will you do it? Will you just continually compare, the last night's data with the data from 3 nights ago and just do that endlessly? Or will it be a finite experiment the way it has been so far?
I think the former is the right answer. We do it endlessly, and hopefully I don't have to do it. Hopefully we teach the computers to do it, right? That's the ultimate goal here. Is I'm not going to be able to search through any fraction of the candidates. So Beatriz has turned up 100 candidates using millions of stars from the existing sort of we would say ground-based archival data, stuff from the 1950s. Every night LSST that is online is going to produce 5+ billion stars. It's gonna observe, and it's gonna try to compare those automatically to its archive that it's already generated. We can only guess how many of these sorts of vanishing candidates are going to be popping in and out every night, but it's probably hundreds a night. So very quickly we'll run out of available astronomers and available eyeballs to chase these things. And that's why we have to start getting really picky about which ones are the most interesting, which ones are the most likely. So being able to put those constraints on how far away could this thing be, or how dim could it have gotten, as you said, those are going to be really important constraints to understand. Knowing everything we can about these objects over the decade will be really important to say, all right, this one is probably some exotic flare star. Interesting, but we're going to throw it out. And we'll be left with hopefully some number that is actually chaseable that we could go after with even bigger telescopes or even more long-term dedicated observations to see if they pop out, or maybe they turned infrared sources, or something that explains what's happened to these stars. Or have they truly just disappeared?
Beatriz, you know, the way disappearing stars might have been found in the old days are not so far in the past, actually, is that you would, you know, have these photographs, and you'd have, here's a photograph from 50, 70 years ago, and here's one from last week, and you put them both into what's called a blink comparator. You put them into a machine, and some astronomer would sit there, you know, ruining their vision by comparing these two things and seeing any that blink because they've changed or they've appeared.
Before you say anything, this is the difference of my glasses before I did the VASCO study, and this is after. 3 months, 1 dioptry.
1 diopter in 3 months. That sounds pretty rapid to me. Okay, well, you see where I'm going with this. I mean, today we have machine learning, right? Artificial intelligence and so forth. Yeah. Will these I mean, how long will it take you to do the VASCO experiment again, assuming, you know, you had the Vera Rubin data and machine learning or new programming that allows you to save your vision?
Well, that depends on how long time it takes for us to set up very reliable code, because it's not the easiest, because we have this 100 objects. It's not a, ideally, one would want to have something like maybe 5,000 transients that you can train your AI data set on. With hundreds, it's a quite small sample in comparison to the 24,000 of objects that we also look through visually. So I guess that once we set it up, it might be a question of maybe 2-3 months to run through all the data. But we're also actually setting up some automatized methods where it can probably go in a few days, but then we also lose a lot of candidates.
Yeah, but I mean, you just heard that James is going to give you 1 billion candidates, you know, at least 1 billion observations, not necessarily candidates, you know, every couple of days. So clearly you've got to automate this to do something faster than every couple of months.
We're working on that. So. Okay.
And does that put you out of a job?
Probably. So that's why I'm
no way it doesn't. Your job is safe. Like, we need the training data. You're absolutely right. I think Beatriz has hit the nail on the head, is that we only have 100 candidates of these things. We're going to have 17 billion light curves. We're not going to know what we're looking at. We need more candidates. I think she's exactly right. We need more training data.
But you say training data, James, right? That's examples, you know, from existing data sets, so that the machine learning algorithms have learned something and then can find things in the new data. But, you know, once he's done the training data, that's like showing somebody how to do your job, and then they usher you out the door. That's my question. Beatriz doesn't seem worried. Okay.
I never think about the future.
So. Well, of course, yeah, who does? But I guess my bigger point here is that this sounds like you've opened up a door that is very, very promising. And the first thing you try to do is what people who are looking for signals from aliens would look for, and that is to automate as much of it as you can. And now you can sit back and wait for the result you're hoping for and book your flight to Stockholm so you can collect your prize.
Actually, we are automatizing it together with the Spanish Virtual Observatory. We have a collaborator there who is he's not using machine learning, but he's using more classical image analysis, and he's doing a fantastic job with getting new transients now, and he's redoing basically the VASCO search that we were doing, but without the catalogs and directly with the images, and the results are really promising.
Let me follow up just a little bit, Beatriz. There have been a lot of ideas coming across the screen here from people who have, you know, their favorite explanations for these disappearing stars. If somebody were to get you, you know, across the table at a dinner and ask you, well, look, I mean, you've had plenty of time to think about what these things might be. What would you tell them?
I would guess on optical afterglows of gamma ray bursts or some type of flares from stars. And that would be my favorite explanations. Is the natural phenomena interesting enough for us to kind of look more into it? It's because of the time scale, that it's really a few minutes. You only have time to they only had time to see it on one plate. Because this plate the red plates had about exposure times of 50 minutes. So that would be my guess, some natural phenomena. I might be wrong, of course, but that's the first things, the first reasonable explanations I would find.
How would you decide?
Well, we are going to do follow-up observations. If we find some infrared counterpart to most of these transients, that would be the M-dwarf flares hypothesis. But some of these, because I've been looking at the amplitudes, and some of these are like, it's like really big changes. Now, if we can exclude that, then we're only left with gamma ray bursts and fast radio burst optical counterparts. And that I'm not sure we're going to be able to kind of sort out very easily. However, it's possible that we will find in some cases some type of counterpart exactly on that spot. And the question is if it looks like an M-dwarf or not. If it doesn't look like an M-dwarf, then it gets much more interesting. And if we find nothing, it's still very interesting for us as well. And if it's lasers, LSST can follow up on these points. If LSST just keeps watching on them, maybe one day it will be seen again. I can also imagine that it's simply things that needs to be monitored during a longer time period, these 100 points.
Okay, so it sounds like what you're saying is, look, here are the various classes of astronomical phenomena that I know about that could produce a rapid change in the brightness of something. So let's one by one eliminate those. But surely, you're going to have a whole, if you will, cascade of these tests. And at some point, you have to allow for the possibility that the only explanation you can think of is some sort of artificial origin, and that you really have found the aliens.
Yeah, if for instance, lasers could maybe give this red transients also on the scene, or satellite glints in the 1950s before the first satellite was sent. I mean, then you would have a UFO flying there or something like that. We can't exclude those things either.
Can you find it? I'll ask this of James. I mean, is this VASCO approach able to find things that are very nearby? People have been suggesting for decades there could be objects in our solar system that bear on these questions.
Yeah, I think the answer is definitely maybe, which is the great science answer. There's a lot of people who are planning to use LSST and the Vera Rubin Observatory to study comets, to study asteroids. So things that we can visibly see moving in the night sky that will be whizzing across the telescope's field of view within each exposure. So being able to track those objects as they trace themselves across the sky is really good bread and butter science for a lot of people, and really important for us here on Earth if we want to stop killer asteroids and understand the origins of life in the solar system. There's lots of good, like I said, bread and butter science that means we want to study comets, we want to study asteroids and things that move. But things that move in unexpected directions, things like Oumuamua, which might be interstellar visitors. This is, I think, a really exciting new avenue. And without wading into the debate about what the origin of Oumuamua was, LSST is the perfect observatory to be discovering one of these things like every month. If they are just chunks of rock or ice floating through interstellar space, we expect to see something like one every month with this facility. And so tracing them as they come into the solar system, watching them as they go out of the solar system, it's a huge opportunity for science. And then, of course, it's a huge opportunity for ET work, for technosignature work. If these things decide to take a 90-degree turn one day, we'll be watching.
Will you be able to, significantly improve our catalog of near-Earth objects, things that might, ruin everybody's whole day by slamming into the Earth? Or is it,
I think the estimate is that within the first month of LSST, we'll discover more asteroids than are currently known in all catalogs. And so there's like fun cataloging issues here where we do keep these real-time catalogs of asteroids, these names, they have these long telephone number like ID numbers. And we've actually broken that catalog already, thinking about how many this facility is going to discover. We need to add more digits to the phone numbers, as it were, because we're going to discover so many little chunks of rock floating through the solar system. And we have to keep track of them because you don't want the same rock to show up a year later and to think you've discovered a new one. You need to keep track of it between exposures and be able to map its orbit. So there's a lot of great computational challenges there when if you only get a couple of quick snapshots of something and being able to predict where it is a year later. It's a great science and math problem. Which there are some really bright minds here in Seattle and elsewhere working on.
That's such an interesting result that's almost guaranteed, I guess you could say, is guaranteed to come out of this instrument. I'm just sort of curious, the proposal that went into develop and build the Vera Rubin scope, what did it have as its number one science motivation? What was clearly going to be beneficial about this kind of an instrument?
I think thinking back to the 90s when this was first planned out, so it's sort of a successor to the Sloan Digital Sky Survey, which we operated in New Mexico here in the US, but just on a much more massive scale. The big motivator there in the late 90s and the early 2000s was dark energy and the origin of the universe. So trying to understand what the distribution of galaxies are very, very far away, so at the sort of edge of the observable universe, and being able to map very deep images of galaxies. Meanwhile, they sort of realized throughout the 90s and 2000s, as we did these kinds of smaller scale surveys, that there are all these things that people like me get our PhDs on: flare stars, things that go bump, things that move. The amazing thing is you build a telescope to study dark energy, and you end up writing papers on comets. And like the origins and the families of comets that are in the solar system. And so it really is an amazing opportunity for everybody to do science. It's not perfect for everything. We're not going to do radio astronomy with it. We still need facilities like the Transiting Exoplanet Survey satellite that discover little transiting planets around other stars. It's not perfect for everything, but it really can impact every area of astrophysics. And I think that's, so I believe, this is me, I don't know, not quoting the website, but I think dark energy is still the number one science priority. But there are working groups in stars and in the galaxy and in planets and then comets, and there's people working worldwide on preparing for the science from this facility in every area of modern astronomy.
Beatriz, how would you describe your own motivation for undertaking this project? This is a big project. I've known people who've done these sorts of surveys, and it's just, and until you can automate it, it's an enormous amount of work. What did you hope to find when you started this?
Well, a star that has vanished, or anything that has vanished. Of course, if I see a big, beautiful spiral galaxy that vanishes, I would be even happier.
Wouldn't be so happy for them.
Well, it's just curiosity. Until I get my answer, I will go on, I guess.
You surely have, in fact, considered how you're going to indeed, and I think we touched on this briefly, how you're going to decide. Every time you do this, it's going to be every 3 days, you're going to find vanishing stars. And, you're going to need some way of recognizing what things are, and are going to have to automate that. And you can only do it on the basis of what we already know, astronomically speaking. So it sounds like in the end, it comes down to the same sort of problems that other people who are doing SETI have, which is, here's a signal that I didn't expect. How do I know whether it's really ET?
Yeah, the first thing one wonders is, of course, could this be some type of instrumental error? If you find a very interesting candidate, you wonder like, is something wrong with this plate? That's the first thing we wonder, and that's the first things we want tests for, if there are some obvious artifacts or some obvious signs of problems. And the next thing one tests for is that if there is some natural explanation for it. And then once you start running out of it, and you wonder if you have missed something, and then you might be stuck for another 1 or 2 years just wondering.
Yeah.
It's so we would actually need to develop like complete scripts to follow on how to handle each of these candidates. We haven't had time to do it yet, but we are learning.
But it's certainly the case. There's a long history of this now, that every time something unusual or unexpected is found in the sky, whether it's quasars or pulsars or stars that get 22% dimmer suddenly one night, that kind of thing, aliens usually get the blame. Often they get the blame because there's no other explanation. But of course, there always is another explanation eventually. But it takes the theoreticians a year to come up with it. So you're okay with that, right? Because you're going to get a lot of funny phenomena very quickly.
That's true. That is true. I can't argue against it.
All right. Well, we have a couple of more minutes here. I would just like, before we turn this over to the audience to ask their questions, and that is, James, the Vera Rubin telescope is not the only, if you will, rapid fire telescope. I mean, Oumuamua wasn't found with Vera Rubin, of course. It was found with another telescope on, I think it wasn't Mauna Kea, but it was Haleakala, I believe, the Pan-STARRS telescope.
Mm-hmm.
Anything you want to say about why this telescope is really the only one or the best one, or something about, I mean, if you're going to find new phenomena, this is the way to go. Build it. It's like the Large Hadron Collider. Build it and you'll find something interesting.
The one thing that the LSST project is going to have that nobody else has is what we would say is depth or aperture. This is an 8-meter telescope. It is unlike any other facility in the world in terms of its ability to look at very faint things. So that puts it in its own class of objects that it's going to observe. That's how it gets to 17 billion stars to study over a decade. But let me take off my LSST hat for a minute and just say that we have a dozen other so-called survey telescopes looking at the most bright stars. Think telescopes that are the size of my coffee cup here. Essentially just camera lenses that are studying the sky, looking at the brightest stars, and they're also doing phenomenal work. And I think if we do our jobs right, if we develop our algorithms to study these phenomenon, if we develop the follow-up capabilities that Beatriz is talking about, where we can take all these candidates and classify them like, that's interesting, that's interesting, the rest of these are garbage, we'll write nature papers about them, but they're not aliens. If we do our job right, these same algorithms are going to work on the transiting exoplanet surveys, and they're going to work on the bright star surveys like ASSASSIN and EveryScope, and there's a bunch of these other acronyms that we can go into, but there are these surveys already operating around the world. So we're developing our techniques here to watch the sort of real-time transients, the sort of 60-second releases that come out. So we've got a test data set right now out of California called the Zwicky Transient Facility, or ZTF. That has nightly alerts, something like 100,000 to 500,000 of these alerts every night. So about factor of 10 less than we expect from LSST, but it's the perfect data set to learn what the garbage is, which just also happen to be good astrophysics. But there are lots of these surveys, and I think if we do our jobs right, the same code that we write to find the aliens in LSST will be operating on, hopefully, every one of these surveys across the world and in outer space.
I like the fact that you said that everything you find that isn't ET is garbage. That's sort of an interesting point of view.
I mean, every one of these candidates is going to be a Boyajian star, or it's going to be a rare R Corona Borealis star. There's a bunch of other things that have right now sample sizes of 1 or 10 or a few. And if we discover 100 of those, that's a revolution in that area of astrophysics. Okay, we didn't discover ET, but it's still its own scientific revolution.
Just very briefly, because we want to go to questions now from the viewers, if you will, our audience here. Well, you mentioned that you can also do surveys of the sky with very small instruments. And one of the advantages usually of a small instrument is you have a wider field of view. What's the field of view of the Vera Rubin telescope?
This is a number I should know off the top of my head. It's something like 100 square degrees per image. So it's wide in a telescope from a telescope standpoint for something so large. It's something like if you hold your hand out in front of you, it's something like the size of your hand or your fist at arm length. It's roughly that size. And so what it's doing is taking this huge mosaic. What's so impressive about this facility from an engineering standpoint is you've got a camera that's the size of a person attached to a telescope the size of a house, moving in essentially a small football stadium size building that is rotating and taking rapid fire snapshots. It's these 30-second pictures. And so this whole facility will just move, well, the top part of it will just move every few minutes and take pictures of the sky. It's a massive amount of glass and metal to be whipping around. And so it's a really amazing thing. But it is the whole goal, the reason it's shaped the way it is it gives it that wide angle. Something like 100 square degrees. All
right, I'm just trying to do the math in my head. Compared to something like the old Palomar telescope, I shouldn't say old, I mean, they still use it. The Palomar telescope, the 200-inch, that sounds like almost 1,000 times more area of sky than you would get with that telescope.
Mm-hmm.
All right, look, we're going to open this up to people's questions. Be sure you put the questions in the Q&A when icon, whatever it is, at the menu item down there at the bottom of the screen, not in the chat. So please do that. The other thing I think we're going to do before you start asking your questions or before we start answering your questions is to mention our poll. We always have polls here, particularly with our connection to Warsaw. And here's the poll question, and it may come up on the screen, so you can choose. Frank, maybe you can put that up on the screen. Here you are. The best way to search for ET, either look at the entire universe, right, such as we talked about here, or search nearby star systems or radios, or flashing lasers, radio signals, or flashing lasers, or just look at our own solar system, because after all, there could be some probe here from some distant civilization just checking us out. So decide what you think are the best, is the best choice. Now, I have to tell you, there's no guarantee that that will have any influence on future SETI, but who knows, it might. So if you do that, while you're cogitating on that, here's a chance that, you know, well, I've already said, you ask your questions. We couldn't get to everybody's questions, of course, when we do this, but we will try and have the best ones. Those will be selected by Rebecca and Frank. All right. Can we go to the first question there, Rebecca?
Yep. Okay, everybody. Thank you, Seth. So we have what we decided to do with Rebecca is to put together questions. So we maximize the chance of having the good answers for all of them. So we have a first question for Beatriz, specifically about electromagnetic information on those disappearing stars. You mentioned follow-up survey, infrared spectroscopy. Can you please elaborate a bit and tell us what exactly you will be able to see by having a follow-up of a disappearing star, assuming that he happened just today? What will you do?
Okay, so let's say I have my ideal candidates. I have this beautiful candidate that was seen in the 50s, in the 80s, and 3 days ago just vanished. So the first thing I will do is I'd apply for this like emergency time at the Grand Tecan telescope, that is a 10-meter telescope, and I will say, oh, let's have a look if it's still there, something still there or not. That would be the first thing. And I would want to say it, for instance, maybe we would look there and there would be absolutely nothing. You look in the optical, you look in the infrared, and there's absolutely nothing, then I would start getting slightly stressed. Of course, maybe you look there and you actually find something. You find something beautiful glowing in the infrared. You can say, oh, maybe they built a Dyson sphere. Maybe they built a Dyson sphere. It could be nice. Or maybe in the case that you find absolutely nothing, just a little bit of radio, but then maybe you have a look at the star from beginning and say, oh, this could have been a yellow supergiant. Maybe it's actually, this was a natural process, because maybe it's a yellow supergiant, it left a little bit of radio there, some radio remnant. That could be a failed supernova. Maybe this yellow supergiant star, against all probability odds for the Milky Way, would still kind of collapse directly into a black hole, and then in 2 weeks there will be absolutely nothing left there, or in 2 years there will be absolutely nothing left there. So these are the ways how we could approach it. I could also follow up with Gaia and see, has it been stable all the time? Was it like perfectly, would the light curve be completely flat before it vanished, or is there a strong variability? And these kind of things could help us to try to figure out what is happening. Because if you see that it kind of is smoothly, I don't know, it gets fainter and fainter and stronger and stronger, and later you see this beautiful infrared thing, maybe you can think about if it would suit with a Dyson sphere build up, for example.
Thank you.
Okay, I was going to ask James to follow up, but I think it's maybe better to go to the next question. Otherwise, we won't get to too many.
Yeah. So the next question is for James. We had a lot of questions when you talk about the Vera, Rubin, and SST. People are very curious to know the details. So what I meant by details is, when will be the first light, when the telescope will start scientific operation, when the data will be processed, when the alerts will be available on everybody's telephone, so they know when there is a new supernova in the sky. Do you have that?
I have some of those numbers off the top of my head. You can, of course, go to, I think it's lsst.org, and they have big fact sheets of everything you could possibly want about what the telescope weighs and what the color they've sprayed on the outside is, and you can find everything about it there. But it's something like, I think we're about 1 year delayed due to the pandemic, just like everybody else. The mountain was closed for a long time. Construction was halted. So the dome is on, the telescope is inside, things are moving forward again. So we're looking at first light somewhere in the next year, and science operations about a year after that. So there'll be about 1 year of commissioning where we're taking limited amounts of data. We're trying to figure out all the ghosts that are hiding in our machines and anything that's in the wiring that we didn't expect, and how we forgot to program something in the software. The data will come out, as I said, the alerts will come out within 60 seconds. They funnel through what we call brokers, certain websites that will, I think, be kind of like space Twitter. They'll basically just be streaming out in real time. And you'll be able to, if you're a scientist or you're an enthusiast, you'll be able to write some simple programs that will watch those alert streams for things you're interested in, that will send you. So there's people thinking of ideas of like, sending me a text to wake me up in the middle of the night because my very magical thing happened. Making sure that whole pipeline goes from telescope to my pocket or to my nightstand. I think that's going to be really important. And the data comes out. The data is essentially free and publicly available worldwide, with some asterisks and limitations on how we move data around the world. But that will come out. I think there's some regular schedule for publishing big catalogs, something like monthly timescales for those catalogs coming out. So it's a huge opportunity for the enthusiasts. It's a huge opportunity for astronomers worldwide at big universities like mine or at small colleges. People can access this data almost every night.
Thank you. Thank you for providing the details. So I'm assuming it's not a question for them, it's a comment on my side. I'm assuming Beatriz will have probably the 100 candidates already ready into the database. So in case one of them reappear, Beatriz will know about that in the next 10 years. Good. So I have another question for you, Beatriz, this time. A lot of people ask about those 100 candidates that you mentioned. Do they have anything in common? Do they disappear?
Yes.
Did some disappear at the same time? Do they move? What kind of analysis you have done in those papers? And can you tell us about it?
I can't answer all questions directly, but I can answer some of the questions. For instance, many of them, and these are 100 independent candidates that have been found. They're from different times of the survey, and they are, what they do have in common is that most of them, not all, but most of them are seen on the red plates, red photographic plates. And most of them are only seen on that red plate, on the red plates, but not on any other plate, which is speaking in favor for that they are something very short-lived, something that appeared shortly and later vanished during the exposure time of the observation. So that is what they do have in common. Then they vary quite a lot in, they are also very strong, I would say, like in comparison.
Beatriz, very quickly, I don't want to, don't give a long answer, but if you see something on a red plate, right, you immediately look at the blue plate for that same era. Okay, so you do that. So what you're saying is that something disappearing tends to be red?
There are two different ways of seeing it. Either it's actually is very red, or we happened to catch them on the red plate because they have longer exposure times. Because the exposure times of the red plates is around 50 minutes, of the blue plates is around 10 minutes. So you have a bigger probability to see something.
It's not color, it's time.
It might, I think so.
Okay, sorry, Frank.
No, I have now a question for James. First, Beatriz, you were done answering to all the questions, to my question. Yeah?
Sorry?
You were done, right? You mentioned did you discuss the proper motion of those targets? But ask if they're close or far away. And do you have any proper motion estimates?
And no, we know that they can't, from the images, we know that we have even blinked the images and tried to check, and there's no chance that they just moved out of the view. Okay. Because they're also point-like, and that's something one needs to remember. Had they been moving that fast, they would be elongated. So it's something very short and not something that moves fast.
Okay, so we have a question. There's something that I did not realize, but it's true. We talk about the Dyson sphere, but none of us clearly say what is a Dyson sphere. So we have a ton of questions about that. what exactly is a Dyson sphere? What the Dyson sphere will look like? Why a star disappear invisible, and you mentioned appear in the near infrared because of Dyson sphere. So James, can you give us kind of a Dyson sphere 101 class?
I can try to give you a short Dyson Sphere 101. Yeah. So the general idea, as it was proposed, is that a civilization would essentially build a giant ball or structure around its star. You might think of pasting on the inside of the structure solar panels, or you could plant plants or whatever you want to do, something to harness that sunlight. So we only get one Earth's amount of sunlight, but we have this whole orbit around the sun that we could build a giant ball or a big bubble around our star and capture all that energy, capture all those photons of light that are streaming off in all wavelengths. So there's a huge energy budget available from the sun if you had one Earth's orbital radius worth of solar panels. That's the general idea. And so the VASCO project, very broadly speaking, is looking for stars that disappear because they've been encased in this giant opaque bubble. Now there's lots of like physical problems with like, where would you get that much solar panel technology? Where would you get enough like rocks or metal to build something this massive in scale? And so there's lots of like practical issues, and this is something that's been researched a lot, is like, would it even be stable? Could you even build a giant sphere with that sort of scale, or would it just rip itself apart from sort of gravitational pull of the star and torque from spinning in the orbit? So there's a lot of concern that a solid sphere is probably not likely, and so a lot of work now is thinking about Dyson swarms or sorts of elongated pieces of structures. So we might not see it fully disappear. We might see it become fainter and fainter as more of these sorts of swarms of chunks of objects get launched, to sort of islands of solar panels get launched into orbit. But the short answer is I haven't built one, so I don't exactly know.
So I saw that while you were answering to this question, we get more and more questions about Dyson sphere. So if you want to know more about Dyson sphere, now we know who to contact, James Davenport. Don't give your phone number though, just give your email address. That will be enough.
You can tweet me your questions.
Okay, so another question, and this is for both of you. And it's a question that it's a bit about the AI algorithm, machine learning algorithm that you mentioned. So the first question is, Beatriz mentioned that you have now a set of 100 objects, and people ask, is that enough to train an algorithm? If not, is there any other alternative so you can start building smart algorithm based on the simulation, for instance? And then I have a second part of this question, which is interesting, is that who is in charge of doing this? Is this work done by astronomers, and how astronomers qualify for that? So multiple questions. Maybe Beatrice should answer the first one, and then James after, if you want. Go ahead.
We have an IT team that have been working on the AI algorithms of the VASCO project in the citizen science projects. So they are in charge of developing the AI algorithms. However, we still have that AI is still in training, and it's going to be in training for a while we are running the citizen science projects. What was the first question? I forgot.
So the question is that enough to have 100 objects for the training data? And if you can run some simulation or play with a simulated images, for instance?
I prefer to wait and collect more objects with the citizen science project. They are not going to disappear, the candidates. So.
Can only disappear once.
What about you, James? What's the state of development at LSST?
This is a big area, because it not just for ET work, but it's of course for everything. We need to know how many binary stars we'll see and how many white dwarfs we see, and so doing really careful simulations, really massive simulations of what we think our galaxy is made of, our best guess. And then on top of that, trying to add this sorts of time components into it, since we don't have a decade survey to attach to these simulations. We're having to make a lot of guesswork. So trying to estimate how many of these flare stars we should see is, for example, is a big effort. So we do have, within the LSST project, we have science working groups that work on this. There are whole PhD theses being written on these kinds of simulations, both for asteroids and for flare stars and for everything. So there's a lot of work going on before the telescope even turns on, because we know that the algorithms are going to be the key to our success for developing the science. Are there enough training samples? No, and I think that's the issue when you have a sample of one or a sample of nothing when we're looking for something that's new. There's no training data, and so on the one hand, we have the ability to search for everything we know, and we can develop training samples for everything we know. But if we're looking for the unknown unknowns, as we call them, we have no training data. And so there's different machine learning approaches to look for those kinds of outliers. There's a whole field in computer science that looks for what is rare and totally unique in a data set. And so there has been the beginning of partnerships between computer scientists and statisticians and astronomers. So I think Beatriz and I are both like proficient programmers, but we're not computer scientists. So our job is to understand what the cosmos are telling us. We do need computer scientists and statisticians and data scientists to come tell us what are our data telling us, and we'll help figure out what the story is of the physics that's going on. That's why I think job security is good. Even though we're going to automate the telescope and automate the software, we need the humans to tell the story.
Mm-hmm. So
Okay.
yeah, just now. One more question, Seth, and then I think, yes, so that's a related question. So the algorithm are not fully ready, especially you mentioned that, Beatriz, as well. So aren't you afraid of being overwhelmed with data or events in the future? And people say, why don't you ask for help? Do you have a citizen science program by chance?
Well, yes, we do have a citizen science project. I can even show if I can find my slides. So I can show how it works. Can I share something?
Yeah, go ahead.
Okay. Did this work? No. Here?
Yeah, now, yes.
So let's see. You can.
Yeah, we can see.
So we have a web page where we actually have both the AI is implemented here and a classical citizen science project where you can where users can help to classify and search for the vanishing stars. Of course, we can. I hope that we are going to be overwhelmed with candidates. We actually are already getting a lot of candidates from the citizen science project. I checked today, we have 35,000 classifications. And now we will need help of probably students, master students, to look through all the candidates we are getting, because it's a lot of work. So yes, we are at risk of being overwhelmed with candidates, but I hope that this is something that one can solve in some practical way. So if people are interested, they are welcome to go to this webpage. I will stop sharing the screen.
Okay, well, lamentably, we can't take all your questions, but you've gotten some information from our presenters about where you might go to get more. You just saw the link for Beatriz's citizen science project. And James said earlier, you should go to lsst.org and check out that instrument there. We have time, well, we don't, but we will take it anyhow. We have time for one more, if you will, lightning question. And lightning doesn't refer either to the voltage of the question or to the speed of it, but sort of the latter. This is a question I hope that you can answer in just a couple of sentences, each of you. And that is something to return to something that we have talked a little bit about, but just a broader picture view of this. Some people think that, these capabilities to peruse big data sets, as demonstrated by what you all are doing here. Oh, yeah, Simon reminds me, we will get to the poll results. We'll get to the poll results, but I did want to do that first because is our normal behavior here. If you happen to not give the result that most people did, you will be excised from the viewing capabilities here. Let me just finish this quick. Well, all right. No, let me finish this question. I think it's better. All right. So we see the application of big data to a very, very interesting problem. But some people have said that in the future being maybe 10 years from now, right, it will be the case that not just astronomy will be done this way, but that essentially all research that involves observations will be done this way. For example, finding the cure for cancer, or why some people are allergic to peanuts, or whatever. And you have these huge data sets, many of them are available right now, and people who have a 5G connection and a cell phone will be able to, with very little effort, analyze these data and maybe find the cure for cancer without knowing the first thing about medicine or cancer. So my question is, if somebody in the audience wants to study astronomy, right, are they choosing the wrong thing, or should they just study computer science? James?
It's an intriguing question. To keep it short, I think there's always going to be a market for astronomers. I think, to go back to your analogy of the cure for cancer, okay, I'm not that kind of doctor, so I won't project what the cure for cancer will be or how it will be discovered. But I would wager that somebody on their cell phone, the citizen scientists, might find the data that reveals the cure of cancer, but we need doctors to tell us that this indeed cured it. And so, to extend that back to astronomy, we have many of these citizen science projects, like Beatriz, like the Zooniverse project, and the LSST program will develop more, I'm sure. This is going to be hugely influential, and if people are interested, there's no better time to get involved as a citizen scientist, as an enthusiast. The data is overwhelming already, which is great. But we still need the physicists and the astronomers and the specialists who are going to spend their careers, hopefully like us, going and studying these and explaining what we see, because we're going to find the unexplainable until we get that magical piece of follow-up data that tells us what the answer is.
Okay, so the astronomy undergraduates shouldn't shift their majors yet. Beatriz, what's your answer to this?
I basically agree completely with James on everything he said. I mean, there's always going to be it's our work as astronomers to try to understand what we have seen. And I kind of more believe into citizen science than I actually believe into the AI, if I may say like that. This might sound quite heretic, but my feeling is that all these automatical things, manners we will have to analyze data will be used to do things faster, but not better necessarily.
You still believe in human expertise. Yeah, okay. All right, Frank, can you show the poll results?
I think Lee will do that. Thank you.
Okay, here you go. Searches for billions of possible, 43%, 48%. Looking in our own solar system is not terribly popular, which surprises me, by the way, because
could you read them, because
not
outside,
not everybody can see.
Will not see it.
I'm sorry. Okay, what's the best way to search for ET? Possibility 1, search the observable universe of billions of possible ET candidates, such as we've been talking about here today, 43%. Answer 2, search nearby star systems for a radio signal or flashing lasers, 48%. That's the leader here, but only by a little bit. That's, if you will, conventional SETI. And the last possibility, search for technologies in our own solar system, maybe some probes that the Klingons have sent long ago, 9%. So, well, okay, that's okay. It sounds like people don't think that we're barking up the wrong arboreal fixture with the kind of efforts we're taking now to find the aliens. Okay, I'm going to turn this back to Simon Steele, and thank you all for your attention.
Well, thank you, Seth. Thank you so much, Beatriz and James. Seth, our master moderator, Rebecca, Frank, and Lee in the background, from which, without whom this would never have happened. Of all the fascinating things that have been discussed tonight, I really like the idea that even though we've got new technology coming into play with amazing new telescopes, we're still turning back to look at 1950s photographic plates and even the glass plates from the Harvard collection that shows that there's still data, there's still science to come out of these amazing history of observations. And I'd even take it back further, the fact that this is just a continuation of the oldest human tradition of looking up into the night sky to search for meaning and to search for stories in the stars. It's just fabulous. So thank you everyone also for joining us from around the world. I got just a few of the countries: India, Pakistan, Portugal, Hungary, Canada, England, Ireland and Scotland, Colombia, Sweden, the Philippines, and Turkey. And from the US, we've got Virginia, Montana, New York, and even somebody from San Jose. So the locals are tuning in as well. Much more important than winning the Nobel Prize, you all get, or you both get, a SETI Talks mugs and patches. So congratulations on the most prestigious award. Frank is showing up an example there on the screen. SETI Institute, as Seth mentioned already, is a non-profit research and education institute. These events, these SETI Talks, are brought to you for no cost. We do very much appreciate donations, and we would like to thank those who have donated during the talk tonight. Thank you so much. These donations really help this program, this free presentation happen. Please do go and visit our website. You can sign up for monthly newsletters and keep up to date with all the work that's going on at the SETI Institute, all the research, and also SETI Talks and other presentations we're going to be doing throughout the year. And with that, I will thank the speakers again and thank the crew again, and say see you next month on next month's SETI Talks. Thank you very much.